Good evening, and welcome to Ramo Auditorium. Welcome to Caltech. I'm Michael Alexander. I'm the Campus Arts and Culture Liaison, and in the fall, we're working very closely with Getty for their Pacific Standard Time project and brought 4 different performing arts programs to campus. And now we're going to be working on our books series called Behind the Books. And we have one movie event coming up in April as well that is part of our Movies That Matter series. Before I get into any of the really important information, we want to remind everybody to turn their cell phones to silent or turn them off. Notice the exits on the back. If there's any other issues, we may bring somebody out on stage to tell you to come out through the side exits here off of the stage, but we just wanted everybody to know where the exits are. I want to thank our sponsors, the Caltech Employees Federal Credit Union, the Friends of Beckman Auditorium. I hope you would consider joining the Friends. We've been able to use some of their support to bring students from high schools to come to the Watson lectures. We've been able to do other kinds of programming with the assistance of the Friends, and so those of you who are able to can consider joining the Friends, and you can find out more by going to events.caltech.edu, and you'll get all the information you need about them. We want to remind you also that Caltech and Beckman Auditorium are the home for the Coleman series. It's a chamber music series that does about 8 concerts a year here, and also want to remind you that that's where the Watson lectures take place. We are going to have a Q&A at the end of this evening's presentation. There is a QR code up on the screen, and if you point your phone at it, you'll be able to get connected to Slido, and you'll pose your questions there, and then I'll be coming back up to field the questions, try and bunch those that look like they belong together, and our 2 speakers will then be able to respond to you as well. But we'd like to start these by having a conversation between the author and one of their colleagues from the campus. And so we're very fortunate today. The author is Kevin Hand. Dr. Hand is out at the Jet Propulsion Lab. He is the planetary scientist where he directs the Ocean Worlds Lab. His research focuses on the origin, evolution, and distribution of life in the solar system, with an emphasis on Jupiter's moon, Europa. From 2015 to 2023, he was project scientist for NASA's Europa lander mission. He is the principal investigator for SHERLOC, the spectrometer on board the Mars Perseverance rover. And his book is called Alien Oceans: The Search for Life in the Depths of Space, which was published in 2020 by Princeton University Press. And we have books that will be for sale for $22, $20 plus the tax. They'll be available at in the lobby at the end of the program, and Kevin will be there to autograph them if you'd like. He is going to be meeting tonight with Victoria Orphan, the James Irvine Professor of Environmental Science and Geobiology, and the Alan V.C. Davis and Lenabelle Davis Leadership Chair and Director of the Center for Environmental Microbial Interactions. So whatever life there might be on Europa is of major interest to her. She is a director in our Geological and Planetary Sciences division. I hope some of you got to go to the Brand Library where the Jet Propulsion Lab was setting up a really incredible exhibit. Did anybody get out there to the Brand? Then you know what I'm talking about. It was an awesome exhibit that was part of this Getty project to look at the intersection of art and science. And I was lucky to be invited to the opening night by the JPL folks out there. And I've been dealing with colleagues there as we were collectively working on the PST, the Pacific Standard Time project. And I made some comment about could there be life at the vents on Europa? And he said, well, you got to talk to Kevin Hand, and there he is. So I went over and talked to Kevin Hand, and he said, well, I guess you haven't read my book yet. And I said, what a perfect idea for our Behind the Book. And I have read the book, and it is a real fun, incredible read. It's not only giving us information, it's giving us background. He's a science historian as much as he is a scientist. And so I think all of you should get the book and pick it up out there. But I right now would like to ask you to all help me welcome to the stage Dr. Kevin Hand and Dr. Victoria Orphan.
Good evening.
Hi, welcome everybody. So I wanted to start off by just saying Kevin and I have known each other for a very long time, back to the time when we were up in Stanford and NASA Ames. And what I loved about the book was hearing a little bit about sort of the young Kevin, the Kevin that got excited about exploration in space and the potential for ocean worlds, translating to the ability to actually go and see the deep ocean on our own planet firsthand. And it was just such a richness, and I loved seeing this arc that you've taken. So I was wondering if you could just tell us a little bit about what sort of put you on this journey.
About the origin?
Yeah.
Well, first, thank you all so much for coming tonight. Obviously, in Pasadena, Altadena area, we've all been dealing with a very difficult time. And then on top of that, as Michael mentioned, my book came out in 2020, April of 2020 of all times. So this, I kid you not, is the first and only live book event that I've done for my book so far. So thank you all for coming out. Really appreciate it. And then on top of that, I want to thank Victoria. As she mentioned, we're old friends, and we've kind of come from different angles at this fascination with the search for life beyond Earth and the extraordinary nature of life that can live on our home planet. I grew up in a small town in the Green Mountains of Vermont, and the dedication of my book is to my parents and the community, where I had a childhood that I like to say was few in fences but full of nets. And what I mean by that is we were just kind of set out to go and explore the woods, find a universe in a mud puddle, just kind of, get into trouble in our own ways, and we did. But the community provided nets. Parents from all over the neighborhood and town were there to help us and get us back on track, which was incredibly important as a child whose curiosity got him into trouble. But my fascination with the search for life beyond Earth really, I think, was catalyzed by an amazing junior high science teacher named Mike Sepperon, with whom I'm still close, and by the stars above the Green Mountains in which I grew up. So that just looking up at the night sky, one couldn't help but be captivated by the prospect of whether or not there's life beyond Earth.
Yes. And I think it's so amazing because I have like the opposite sort of experience in looking through a microscope and seeing this amazing diversity of life in a drop of water, and taking me to the depths of the ocean, and then from there thinking about the extremes of life that lives at the depths, and taking me to thinking about what could potentially be out there off of Earth. And so it's very fun to see these sort of like divergent paths come together and to bring us here.
Yeah, the microbes in the microscope, stars through a telescope, as you enjoy saying.
Yes.
A lot of parallels, and sometimes you can even compare images, and it's hard to tell them apart.
Yes. So for those of you who haven't had a chance to read the book yet, so Kevin starts this whole thing off with a cliffhanger of his experience getting to do his first dive in one of the Russian submarines, the Mir submarine, as part of James Cameron's big expedition, right? And his first dive, he talks about running low on battery power, and this being a very concerning experience. And of course, having done a lot of diving myself, it was bringing up all these sort of memories of these unexpected things that can happen at the bottom of the ocean. But I was thinking, I've never had that happen on my very first dive. And so I was curious, like how you handled that, because I'm sure that's not a normal circumstance. Yeah.
Yeah, and so this, I got to make 9 dives to the bottom of our ocean, the Pacific and the Atlantic, in the Russian Mir submersibles. And it was an absolutely extraordinary experience. But Victoria that's what she does as a profession. She's taken several dives on Alvin. I was way out of my physics and astronomy depth. Growing up in the mountains, I feel very comfortable in the mountains, but get me on a ship back in those days, put me in a submersible nonetheless. And I never got claustrophobic. I grew up caving and exploring small spaces, including well-decorated cardboard boxes. So the submersible part didn't concern me as much as just this kind of unknown realm. So yeah, I go down to the bottom of the Atlantic, and that experience in and of itself, you and I have talked a little bit about this. Let me just forward here. We've got a few slides. I can show you. Here is one of the Russian Mir submersibles. 3 people fit in this thing, which is the same for Alvin,
yep.
Right? That's me in this Russian submersible. And I had kicked the tires on this before we got into it to go down. And the pilot, Victor, who did not speak much English, he assured me that if anything went wrong, there was a big wrench under the seat on top of which I was sitting. And all we needed to do is pull that wrench out and just undo this nut and bolt, and some ballast would drop. And then we would just float back up to the surface, and we'd bob around like a cork, and eventually we'd be recovered. So, okay, thank you, Victor. That's
Look for a handbook, because they gave us like the safety handbook.
Oh,
They
there was
said
no handbook
If the
with
pilot
Russians.
became incapacitated, you could look at the quick instruction sheet on how to, yes.
Oh, if the pilot became, yeah, I hadn't thought that far ahead, if the pilot became incapacitated. Well, on this particular occasion, we got down there, and Victor just parked the submersible on the bottom of the ocean. And I was like, okay, what are we doing? Low on power. Okay. And there were 2 submersibles, Mir 1 and Mir 2, and we had lost track of the other submersible. And yeah, and part of the reason you dive with 2 is just in case something goes wrong with one, you got the other one nearby. And so, yeah, Victor just parks it, and then he starts shutting off things. Shuts off the lights and various stuff. I'm like, okay, what's the other person in the sub, Mike, he and I looked at each other, and we're starting to get a little bit nervous. But, Victor's experienced. And then Victor points to this little thing that looked like a bucket of kitty litter. And he said, not working so well. I'm like, Mike, what's that? Mike goes, I think that's the CO2 scrubber. Like, wait a minute, the CO2 scrubber is not working that well? So we got a power issue, now we're running into a breathing issue. But Victor, he obviously had done many dives, and so we just sat there at the bottom, basically with this thing powered off. And eventually, the other Mir submersible came around and located us. And in that Mir submersible was James Cameron, the film director, because we were down there doing this IMAX documentary. And I knew that Cameron had a big old camera on the end of the robotic arm. So I wrote "must surface" and put it up against the little window. And so I held it there with the confidence that Jim and the folks in that sub would see the sign and signal to the Keldysh, our mothership, that we needed to surface. And so after a little while, Victor felt confident that we could release some ballast and head on up. So we survived, obviously.
You didn't have to use the wrench.
Didn't have to use the wrench. We didn't have to get rescued. And the Keldysh found us that night, which was part of the issue too. He didn't want to go up without the ship knowing that we were surfacing, because it was nighttime and it was going to be particularly tricky if we were just bouncing around. But so if I forward here, this is what the mirror looks like on the bottom. Victoria, which I gotta say, as much as I'm excited to talk about my book, Victoria is an incredible award-winning microbiologist who's done all sorts of amazing things, including many dives on this. And you were telling me about one time recently when you lost power.
Yes. We were up off of Alaska, and they had just retrofitted Alvin to go down to 6,500 meters, and we were one of the first sort of legitimate science expeditions to take it to some of its sort of maximal depths. And so we were exploring some places where methane was coming out of the seafloor off of the Aleutians. Very, very exciting, really, really frigid cold. And they apparently hadn't been taking Alvin to those depths since they had done the engineering dive. So we were sort of the guinea pigs in pretty inclement weather. And so during my dive, we had what was called a brownout. So the power actually went off. And if you've ever just been frustrated with your computer, watching it go vroom, like the entire sub, all of the screens just went vroom, and the emergency lights went on. And we had that sort of like wide-eyed look, the other scientists and I, and trying to stay calm. And we figured it out, and we limped our way along and collected one tube worm and then surfaced. So,
which is good. You got some science done.
We did. Yes. But it gives you a great appreciation for when the technology is working well. It's almost like you're going on a great adventure until something doesn't work, and you realize how much technology and challenges there are in working in these kinds of remote environments, right?
Yeah.
And it's even worse thinking about trying to do this on a body off of Earth, right?
Well, let me ask you, what is your favorite part of your dives?
Oh, all of it. So what I realized is I actually love the pinging, the sonar pinging and everything. Like if anybody's ever been to Disneyland and the little submarine ride thing, like it's kind of like that. I mean, it's much better than that, but it has that feeling. And when that pinging stops, like when you have problems, you realize just how alone you are, but it adds to the excitement. So it's the whole deal, seeing the bioluminescence out of the viewport, hearing the pinging. You know, you're not communicating much with the surface, so it's a very peaceful experience, and you're there to do your science, and you're seeing things that nobody else in the world has had an opportunity to see. So, I mean, what could be better than that? You know?
Yeah. That part with the bioluminescence, so is that one of the
Yes.
portals? Yeah, off to Victoria's, I guess it's her right in the image there. But as you're going down through the ocean, you can put your face up to the portal, and you go through the sort of photic zone, the region where sunlight penetrates. And then as you transition to the darker depths, the turbulence of the submersible dropping through the water causes bioluminescent creatures to excite. And so you see this sort of upward flow of biological fireworks as you're going down, and it's just a magical display.
It's really magic. and it gives you a sense of just how much life, the oceans are just rich with life, and most of it is things that you can't see with your naked eye. And so, I mean, there's just an amazing amount to be discovered. Yeah. Yes. So I was also curious, it fascinates me, both of us are scientists, and of course we communicate our research in science through writing manuscripts and giving talks and stuff, but very few of us decide to do something like write a book for the general public, which, in this particular case, I know that there was a significant amount of effort that went in there to research and pull this together, and I'm just kind of curious, like, what compelled you to do this?
Yeah. Well, I love writing, right? I guess you can write a book if you don't like writing, but I do love writing, and I felt like there was a real niche. Over the past 60 plus years of exploring our solar system with robotic spacecraft, many of which were obviously built and operated by JPL, one of the most profound and exciting discoveries that these missions have enabled humanity to make is the discovery of oceans beyond Earth, these so-called alien oceans. And think about it, with the first Mariner flyby of Venus, and obviously even before that, we knew that atmospheres existed on other planets. We knew that atmospheres were kind of a widespread planetary phenomenon. And for many years, that was the focus of a lot of planetary science research. And our study of worlds like Venus helped inform our understanding of the greenhouse effect, climate change, et cetera. Fast forward to today, and we have really good confidence that many oceans exist beyond Earth. In other words, oceans are, at least in our solar system, a relatively widespread planetary phenomenon. And in the decade or decades to come, we actually will engage in sort of a new field of comparative oceanography, where we'll be able to kind of look at our ocean in the context of these other oceans. Now, granted, these other oceans are trapped under ice shells, but still there's a lot of interesting fundamental physics and chemistry and geology that connects our ocean to these distant oceans. And that's not even bringing up the topic of biology and the search for life. So I wanted to write this book just to get my own excitement and interest in this topic out there. And as a kid, I was a passionate reader of Carl Sagan and popular science books. And I wanted to get a book out there that filled this niche for the young me, the young you in high school or college, to get them excited about this field.
Yeah, and one of the things that I really appreciate that you carry forth in this book is this historical perspective, and especially like shining a light on many of the unsung heroes in science that participated in many of the fundamental discoveries. So from the Challenger expedition, highlighting some of the women that actually dove, like Gloria Hollister, and people that I didn't even know. Like, I learned things from reading this book, which was just really amazing. And this poetic chapter that you have about the rainbow connection and the importance of spectroscopy, and the passion of a monk that made glass, right? and how that sort of kicked off the whole field and enabled our ability to be able to identify chemicals on other worlds. So that, I'd love to hear a little bit about the monk in particular.
Well, yeah, as scientists, one of the things that we do as scientists is we just follow our curiosity, we follow our nose, we go down rabbit holes, whether it's a specific compound or process or whatever it is that we specify. And in writing this book, my scientific nose caused me to go down many rabbit holes in the history of science. And as a spectroscopist, so much of what I do in my lab is infrared spectroscopy, some Raman, some visible, et cetera. And we all learn about Fraunhofer and Fraunhofer lines and kind of the basics of his contributions to the foundations of spectroscopy. But then I found myself asking, well, okay, Fraunhofer used these prisms to spread apart light from the sun and from candles, et cetera. Where did he get those prisms? How were prisms made back in the early 1800s? And so I went down the rabbit hole, and it turns out that Fraunhofer worked with in this Benedictine monk monastery in Bavaria. And the monks took glass making incredibly seriously because, and it's obvious once you dive into it, think about all the cathedrals and all the glass that is used in religious ceremonies and buildings, the stained glass windows. And so Fraunhofer's kind of secret sauce were these monks that were incredibly meticulous and careful with the flint glass and the crown glass and making very specific density glass that Fraunhofer could then use to investigate in fine spectroscopic detail the light coming from the sun. And so, yeah, I think I liken Fraunhofer to sort of Steve Jobs of the day with his cadre of monks that helped make the incredible prisms the innovation of the time.
Yes, so great. Okay, can we talk about the new Goldilocks zone a little bit? So, you spend a lot of time, the beginning of the book also, sort of introducing how we know that there are ocean worlds off of Earth, right? And this sweet spot of habitability. And I'm really I want to hear more about how we know what we know.
Right. So this, of course, is Europa. And when we were students back in high school and college, et cetera, coming on up through the 80s and 90s, and I guess it was really, so it was the late 90s when the Galileo spacecraft first started sending back images like this. And the Voyager spacecraft sent back beautiful images of Europa and Enceladus, a moon of Saturn. And that was the late 70s. But really for many of the decades, much of the past half century or more, when we've been searching for life in our solar system and beyond, the framework has been kind of set by this Goldilocks scenario, where in order for a world to be habitable, you have to be at just the right distance from your parent star, in our case, the sun, so as to maintain and sustain liquid water on the surface of your planet. In other words, an ocean on the surface. If you're too close, like Venus, you boil off any water that you once had. If you're too far away, like Mars, you freeze out a lot of water. Mars, of course, lost a bunch of water to space. But if you're at the Earth-Sun distance, then you're at that kind of Goldilocks zone, that sweet spot. And so for decades, this kind of planetary Goldilocks scenario where the energy for maintaining liquid water is mediated by energy from your parent star, that was the framework for habitability. But worlds like Europa and the large moons of Jupiter, shown here, are giving us a new Goldilocks, a Goldilocks for habitability, where the energy for maintaining liquid water oceans comes not from your parent star, but rather from the tidal tug and pull that these moons experience as they orbit worlds like Jupiter and Saturn. And so in this new Goldilocks framework, which is well exemplified by the 4 large moons of Jupiter, Io is kind of like Venus. Io is the most volcanically active body in our solar system. It does not have a liquid water ocean. It's got too much energy. Callisto, the furthest out of Jupiter's large moons, is a little bit like Mars in this scenario. Callisto, we don't think has much tidal flexing. It may have enough energy from radiogenic decay of heavy elements to sustain a bit of an ocean, but it's a big question mark. But Europa and Ganymede, and Europa in particular, really occupies this new Goldilocks zone, this new sweet spot for habitability, where the tidal flexing of Europa as it goes around Jupiter on its slightly elliptical orbit creates enough internal heating to then sustain that liquid water ocean underneath the insulation of its ice shell.
So you were saying that just from tidal flexing alone can create enough heat.
That's right.
So here we get heat from the sun, right? That's the driver.
Yep. On the surface.
On the surface. We have tides, but
right.
Why aren't we like boiling over?
well, so in our case, we're orbiting the sun on a pretty circular orbit. And our moon and the Earth do this dance where we basically have a perpetual bulge of water that follows the moon and a bulge that doesn't follow the moon on the opposite side. And so the moon kind of carries that around, creating what we experience as the tides. Jupiter is some 318 times as massive as the Earth. And Europa is about the size of our moon. And so the tides on Europa, if you could stand on Europa, which you wouldn't want to do because the radiation environment is pretty extreme and you'd die after not too long on the surface. But if you could stand on Europa's icy surface, by some calculations, you would rise and fall by about 100 feet every time that Europa orbits Jupiter, which takes about 3.5 Earth days. And so that's the power of Europa orbiting Jupiter, this incredibly massive gas giant. And as you and I love to talk and daydream about that heating, that internal heating, may not only maintain a liquid water ocean, but it also could possibly give rise to an ocean floor that has your kind of environments.
Fun hydrothermal systems producing all sorts of great chemicals that, at least the life that we know it on our own planet, like the microbes that I happen to love deeply, can use, right?
So tell me a little bit about that. I'm going to show, this is a picture that I took of one of the hydrothermal events that I visited. And in kind of the same way that worlds like Europa turned habitability of other worlds upside down, the discovery of these systems changed.
Right. So 1977 was this big turning point, and there was an oceanographic expedition, and you have this great line in the book that was, they went out really to understand something fundamental about the geology, and they came back questioning how biology worked. And that was because, and there wasn't many biologists on this expedition, mind you, but they went down there and they pulled up some material from these hydrothermal vents. This was off of the Galapagos. And they found these bizarre organisms, giant clams, all sorts of things. And of course, they don't know what to do, and they're trying to figure out. And back then, you could drink on the ships, and so they were like trying to preserve these things in vodka and bring them back to the scientists on shore. And up to that point, it was believed that life in the deep sea was fueled solely by photosynthesis. So all the organic carbon that fed the deep sea was produced at the surface and would trickle down. The deeper you were, the less food you would get. And so to find these density, these oases of life that are not just surviving but thriving in these seemingly inhospitable places was just like a really eye-opening experience. And it turned out that the way that they're doing it is they've teamed up with microbes. They have symbionts that are breathing all of this noxious hydrogen sulfide, methane, and those symbionts can fix carbon dioxide just like a plant can do, but they're using that chemical energy and they're feeding it to these animals, right? That was unheard of, right? That was bonkers biology. And so, even on our own planet, right, changing your perspective gives you a whole different way of thinking about when and where life can survive and thrive.
Victoria sent me this great
cartoon,
cartoon that really puts it in perspective.
Right. Yes. Yes, so again, just changing your perspective. So, yes, yep. So it's really, you don't have to go far to really realize just how wondrous and how little we understand about life, even on our own planet. So it opens up that much more richness to think about other places even that we haven't explored off of Earth.
And that discovery, as Victoria mentioned, 1977, at that point in time, NASA had the Viking orbiters and landers on the surface of Mars, searching for the first time for life on Mars, which obviously has continued to be a major focus of our exploration right on up to the present. This is the Perseverance rover, and you can see two little holes in the rock that Percy is looking down at. We collected 2 rock cores and cached them underneath the rover there. And I think one of the things that you and I really find exciting about these alien oceans beyond Earth is that, on a world like Mars, this site billions of years ago was covered in water. This is Jezero Crater. Once upon a time, it was a lake. We're down at the bottom of Jezero Crater in this particular image. And then over the past several years, we've roved up this ancient delta looking for signs of past life. And the search for past life on Mars is extraordinary. But it's going to be hard to find large biomolecules like the ones that Victoria loves to study, the DNA, the RNA, the proteins, et cetera. Those don't last long in the rock record. Whereas when we do get out to Europa, Enceladus, Titan, these are worlds where extant life could exist. Life could be alive there today. And that's a real game changer, because that means that if we do find life, we can ask the question, did the same biochemistry occur on this far and distant world? Does life on Europa or Enceladus or any of these alien oceans depend on DNA, RNA, proteins, or is there another biochemical game in town? Is the origin of life easy or hard? Is it contingent or convergent biochemically? We just don't know. And as much as I love Mars, that's a hard question to ask there, but it's a prime question that motivates our interest in worlds like Europa.
Yeah. And there was another piece of this too, right? It's also the distance of Europa to Earth relative to Mars, right? So you made the case in the book that if you want to truly understand whether or not there's an independent origin of life, you have to sort of take it outside of the realm of possible, interplanetary transit, as much as that may be crazy to think about, right?
Yeah. So one of the great benefits of Mars for us is that it's nearby and we can send robots there on a relatively rapid cadence. One of the downsides astrobiologically is that in the early history of the solar system, impacts on Earth likely sent ejecta to Mars, and impacts on Mars may well have sent ejecta from Mars to Earth. And it's plausible, even if somewhat improbable, that microbial hitchhikers on Earth could have seeded life on Mars or vice versa. So even in the best case scenario of, say, finding life on Mars that's alive today in some subaqueous environment, if that life was based on DNA, I think we would have a very hard time convincing ourselves that life on Mars represented a second independent origin. Whereas given how far out Europa is, given how far out Enceladus is, I think even if we found DNA-based life on those worlds, I at least would likely, from a parsimony standpoint, tilt towards that DNA-based life representing a second origin and the biochemistry of amino acids, of nucleobases, of DNA, RNA, proteins being kind of a convergent solution for the origin of life and biology. And so that, again, motivates much of our excitement and interest in these worlds.
Yeah. A lot of these missions take years in the making, right? And I think about it, when I do science in my lab, maybe we're doing an experiment, it may last 5 years, maybe even 10 years if we have something that we're really following over time. But to do space science usually requires huge teams of people. You're in the proposal stage, you're dedicating your life, you're in it, and many times they don't go forward. And I wonder, it's a very different way of doing science, and I'm just curious, how do you cope with that, and how do you go forward?
Trying to depress me.
Yeah, sorry.
These, I think for many of us in this realm, this business is not for the faint of heart. I see many JPL colleagues in the audience, and these missions, whether it's the early Ranger spacecraft on up to Perseverance and Clipper, and hopefully someday a lander on Europa and Enceladus, et cetera. These missions are the technological cathedrals of our day, and they are generational tasks. And as much as you hear the mantra of, failure is not an option, that's true once you get to the launch pad, et cetera, but in the lead up, failure has to be an option. You have to put yourself out there. You have to try and get these extraordinary missions done with the hope and aspiration that you can change humanity's understanding of the universe in which we live. So, I've taken it on the neck a number of different ways with failures, but you got to pick yourself back up with, images like this, photographs like this. Here's the Clipper spacecraft.
So the Clipper is going, right?
The Clipper, thank goodness.
And it's supposed to arrive when end of the.
So again, not for the faint of heart. This mission launched on October 14th of 2024 after a hurricane and I guess several tiny tornadoes tore through Florida. And I first started as a team member on the science definition team for this mission, or what would become this mission, in 2006. And it just launched this past fall. And we've had a variety of permutations of orbiters, flyby missions, landers. And so when Clipper got off the launch pad, that was a very emotional experience.
Yes.
Many of us were just like tears coming down and speechless. It even kind of gets me a little choked up just looking at that picture.
And so what sort of science and discoveries might be possible with the type of technology Clipper mission is planning to carry out?
So Clipper will arrive, it'll enter it'll start orbiting Jupiter in 2030, and it will begin its prime mission of flying by Europa in 2031. It's got to pinball down a little bit after it arrives in the Jovian system. And so Clipper will be on a roughly 2-week orbit around Jupiter, and once every 2 weeks, we'll do a close flyby of Europa. The engineers, the pinball wizards, as I like to call them at JPL, are able to get the Clipper spacecraft within about 100 kilometers, even within 50 kilometers of Europa's surface, which, as a scientist, I'm just so grateful to them for being able to pull that off. And with each flyby, the cameras, the spectrometers, the ice-penetrating radar, the mass spectrometers, the particle detection instruments will all be running at the same time, looking at the same swath of Europa's surface. And from that data, in particular, the spectroscopy, both the light spectroscopy and the particle spectroscopy, the mass spectrometers, we will be able to very thoroughly characterize the interior of Europa, the existence of its ocean first and foremost, and potentially how thick the ice shell is, how deep the ocean is, and compositionally, depending on how generous Europa is with its oceanic composition, we have the capacity to find large organic compounds. And if Clipper finds large carbon compounds, then it's game on. We got to get out there and explore this world in great detail to search for signs of life. And we already know quite a bit. Much of the work that I've focused on in my lab and collaborations with my colleague Mike Brown here on campus and some amazing grad students, we know that Europa's ice, the sort of the reddish, orangish coloring here, we know that at least some of the color that we see on Europa is caused from salts from the ocean below coming up to the surface and then being irradiated and changing color. Spectroscopically, we can very convincingly say that some of that along those fractures, some of that material is salts. So we know the ocean is expressed on Europa's surface. With that high-resolution camera, will we find a European octopus? Probably not, but I can I can stay optimistic.
Yes, so that brings me actually into the more speculative part of your book. You have a chapter that is called "The Octopus and the Hammer," where you talk about the potential for intelligent, complex forms of life in a European ocean. And so I felt like that would be a fun place for us to end before we open it up for questions from the audience. I just want to hear what you think would be these types of adaptations that might promote this kind of intelligent life, should it exist.
Right. So I'd sort of, in I think it's chapter 12 in my book, pursue this thought experiment of, well, if worlds like Europa are ubiquitous throughout our galaxy, throughout the universe, what a shame if evolution could not proceed to intelligence, tool use, et cetera, because that's a lot of very habitable real estate. And so I kind of explore the idea of what would it take for multicellular life to evolve on a world like Europa, and then might a European octopus someday figure out how to use a tool to develop a forge around a hydrothermal vent. And so I get very speculative. It was one of my favorite chapters to write because I just kind of let my imagination flow. But the facts are that it's really not that crazy of an idea for the following reason. when you look at the kind of evolutionary pressures on Earth, much of the way we think, or much of the reason, or the way in which planet Earth helped make multicellular life possible, and eventually civilizations, is through the availability of oxygen in our atmosphere. And oxygen just changed the game when it came to the energy available for biology on Earth to do the complex things like organize from a multicellular standpoint, to develop brains and nervous systems. Well, Europa has got this really curious oxygen production system going on, where its icy surface is being bombarded by electrons and ions from Jupiter's magnetic field. That splits apart some of the water molecules, the H2O, and some of the oxygen recombines to form O2. And we know with ground-based telescopes, with spectroscopy, that oxygen is trapped in the surface ice of Europa. And so if some of that oxygen in the surface ice gets subducted down into the ocean below, now maybe you have a way of oxygenating Europa's ocean. And if oxygen is available, maybe there's a way for microbial life to start to come together and undertake symbioses and maybe eventually arrive at an octopus. But again, it's a highly speculative chapter, but hopefully those of you that have read it enjoyed it.
Yes, yes. Okay. Do you think we can open it up for some questions from
Absolutely.
the audience?
Yes.
Yeah. All right.
To open it up for some questions, I'm going to ask that we put the slide back up that shows the code. There it is. And while some of you are pulling that up onto your handhelds and composing your questions, Victoria, do you have another question, or were there any other things that we should cover here? Because we're going to have to take a couple of seconds before we get
Sure.
audience's questions
yeah,
on my handheld.
I would love
here.
to come back to our own ocean. It's amazing to me that the majority of our deep ocean has not been explored, right? And we probably know more at this point about the surface of Mars than we do about our own ocean. And you talked a lot about the historical use of Navy vessels and things for exploration, big and bulky types of equipment to explore the deep ocean, which is just fundamentally different than the way that space science is done, with sort of smaller, light, cheaper material, maybe not cheaper, but, and how we might be able to port some of that technology into our ability to understand more of our own, ocean world.
Yeah. Well, and this is a question, how do we leverage what we're doing in space to advance the exploration of our home planet and our own ocean? This is a question that motivates much of the collaboration that Victoria and I have pursued over the years. And it's a really important and interesting one because when it comes to space exploration, we are governed by the tyranny of the rocket equation, as it's often put. For every gram of mass that you want to put on the surface of Mars or flying by Europa, you also have to include however many grams of mass of fuel to get that gram of spacecraft to its destination. And so aside from the brilliant engineering and innovations that we do here on campus and up at JPL, really one of the key things that we're very good at is making complex instruments and other things very small, very lightweight, and it does cost a lot to do that, no doubt about it. But we've got these instruments that fly to other worlds that are highly capable. And part of what we're trying to do is teaming up to see how we can bring some of that space technology into our own ocean, making smaller, autonomous underwater vehicles that are highly instrumented, that you could just throw out from shore, so you don't need to rent a big ship. You don't need to pay many, many tens of thousands of dollars per day in ship costs, et cetera.
And they're just fundamentally limited, right? There's not that many research vessels for people to go out on, and so, but there is a lot of shoreline, and it would not be too difficult to really make a lot of progress in exploration and being able to do time series studies.
So I think there's a really nice convergence. We started out talking about microbes and stars and the convergence there. The path forward, there's a lot of kind of technological convergence that I think will help us advance the exploration of our own ocean while building a bridge to someday deploying a submersible under the ice of Europa.
Wouldn't that be cool?
This computer nerd hit the wrong button, and I need the help to find the questions again. So, here's the first one I'm going to go with. Will you benefit from results of these missions in Europa in your scientific lifetime, or will it take so long to get there that they'll have to be the job of other future scientists?
Yeah, that's a great question. By the time Europa gets there, I will still be part of the science team, but it will be the younger generation that likely analyzes the data and writes up the results, and I'll just pat them on the back and say, good job.
Here's a question. I'm curious about Dr. Hand's thoughts about the APL Dragonfly mission. Do you think that this success of this mission might open up new avenues for surface exploration? And maybe be better explained to some people about the Dragonfly.
Right. So I'm a scientist on the Dragonfly team. The Dragonfly mission is this truly extraordinary and ambitious mission to send the spacecraft, and it'll launch somewhere in 2027, 2028 timeframe, and it will go out to Saturn's moon Titan, which has a thick nitrogen and methane atmosphere. It will deploy a parachute to go down through much of the atmosphere. It will then get rid of the parachute, and out will pop 8 rotors, and the Dragonfly spacecraft will turn into essentially a drone, and then it will fly to a landing site on the surface of Titan, after which we'll then spend time sampling Titan's surface, and then we'll hop with the drone to another site and another site and another site. And Titan is kind of this wild card astrobiologically. Titan's surface is at just the right temperature and pressure so as to make it possible for liquid methane lakes and seas to be stable. And when people ask me about the prospect for weird life unlike anything that we've ever seen on Earth or that we might find in the liquid water ocean of Europa or Enceladus, when people ask me about kind of thinking outside the box biologically, I point to Titan because of this hydrocarbon chemistry. It's the liquid methane. For life to arise in that goes beyond anything that I as a scientist can develop an hypothesis for. But who knows? Mother Nature does not care what I think or how clever I or any of my colleagues are. Mother Nature is there to surprise us. So there could be very, very weird life on Saturn's moon Titan, and the Dragonfly mission could find it.
I don't completely understand the question, but it seems like a good one. Over what time scale does the power of tidal heating significantly affect orbital energy?
That's a good question, and I'm not entirely sure I've got a great answer for that. We're still, well, I can constrain it for you. On Europa,
It's within the time scale of Europa's orbit around Jupiter, which is 3.55 days, roughly 86 hours. And so we know that something must be happening on that time scale. But the three innermost of the large satellites, Io, Europa, and Ganymede, are captured in what's called the Laplace resonance. So for every one time that Ganymede goes around Jupiter, Europa goes around Jupiter twice. And for every one time that Europa goes around Jupiter, Io goes around Jupiter twice. This resonance means that there's an alignment where these three moons kind of pull on each other and maintain the slightly elliptical orbits. And that's incredibly important because you don't get much tidal heating if you don't have an elliptical orbit. And many of my friends and colleagues have modeled sort of the time history over billions of years of this resonance coming in and out and how much heating might occur. And so we think there might have been times when tidal heating was much more significant on Europa and maybe much less. And we just don't understand that yet, but hopefully with the Clipper mission, we'll gain more insights into that. So it's a really nice question.
How many planets have you studied for searching for life?
Oh, I've given them all some consideration. Who knows? There could be life on Pluto. There could be, there was this classic National Geographic book, and I think Carl Sagan once pontificated about hot air balloon animals in Jupiter's atmosphere. And so I certainly hope that when it comes to biology, Mother Nature is much more creative than our kind of water and carbon-based paradigm here on Earth leads us to kind of make predictions about habitability. But within our solar system, my favorite candidates are Mars, Europa, Enceladus, and Titan. And then Ganymede, and maybe throw Pluto in there, dash a Mimas, I don't know.
What are the biggest challenges to us doing a lander mission on an ocean world? Technology, policy, finance, interest from the scientific community?
Yeah, this is a question that's definitely near and dear to my heart for many years. I helped lead the effort to get a lander to the launch pad to go to Europa. And I can say with a good degree of confidence that it's not technology. There's no magic wands that we up at JPL or APL or Goddard need to invent to make it possible to land on Europa or Enceladus or Ganymede or any of these worlds. The technological know-how is there. It really is a convolution of oscillations in funding and science priorities and all of those kind of non-science and technological factors.
Is the ice on the surface of Europa constantly breaking due to the 100-foot heave cycles?
Yeah, we don't know. We have looked, my colleague Cynthia Phillips at JPL, for years she helped kind of look for changes in the ice of Europa, comparing images from the Voyager spacecraft to the Galileo spacecraft, and more recently the Juno spacecraft. And so far, she and various teams have not found an obvious new fracture in the ice of Europa. But my goodness, when we get out there with Clipper, with the high-resolution cameras that will be able to image at 0.5 meter per pixel, I think we're going to see some new and extraordinary things, new fractures, new melt-through regions, plumes potentially. I'm really excited to get back out there.
I want to thank Anonymous for sending in so many questions, by the way. Are there known mechanisms other than radiation from a star or tidal forces that could maintain liquid water on an other body in the universe?
So those two are primary. The third that I would mention is decay of heavy elements. Uranium, thorium, potassium to some degree. Early on, aluminum-27 is quite useful. Radiogenic decay is a good heat source. The problem is having enough of those elements in your core or mantle so as to maintain liquid water for, after several billion years, because a lot of those heavy elements deplete on a timescale of a few billion years, and so by the time your solar system gets to 4.5 to 5 billion years old, like ours, your radiogenic decay gets to somewhere in the range of 10 milliwatts per square meter, which is kind of what we see on the moon in terms of just energy coming out of the lunar crust. Whereas, say on our seafloor, it's somewhere between 60 and 80 milliwatts per square meter. Meanwhile, predictions for Europa's seafloor, given the tidal energy dissipation, range from tens of milliwatts to many hundreds of milliwatts per square meter. So yeah, radiogenic decay is kind of the third source, but once you're billions of years in, it's probably not that useful.
Over what time scale does the power of tidal heating significantly affect orbital energy?
We kind of answered this one, right?
Did we?
Yeah.
Okay. Well, I have one for you. How did the scientists discover that the monks were doing this work that led them to understand the spectaculars?
How did Fraunhofer team up with the monks?
Right, yeah.
That's a good question. I don't quite know like his origin story with starting his work there. He did not go to college. He was a craftsman. And so I think it might have just been proximity in Bavaria early on. And kind of seeking out some of the best glass, but yeah, I don't know, Michael.
Could you expand on possible subduction of materials and possible plate tectonics of the ice sheet?
Well, there again, so all of these fractures that we see on Europa have created a bit of a puzzle. Because these fractures, if I just go back to this image, for the most part, these look like pull-apart zones, regions where the ice is coming apart or maybe strike-slip motion is occurring. And if all you ever have is regions that are pulling apart from each other, that means that, well, you are increasing surface area. And that doesn't make sense. There must be some areas on Europa that are subducting. There was a really nice paper published by my colleagues Simon Cuttenhorn and Louise Proctor a number of years ago, where they identified some areas where they think they could show some surface loss, making a case for subduction. But when we get out there with Clipper, that's one of the things that the Europa geologists will be looking for right off the bat. Where is the ice going and how is Europa's surface being resurfaced?
We've got a one-word question here with 3 question marks. Aliens?
Aliens. I don't know quite what's meant by each of those question marks. I'll interpret it as how likely do I think it is that we will find life within, say, the ocean of Europa or on Mars or Enceladus or Titan. You're often sort of said, well, what does your gut tell you? And there's this famous quote from Carl Sagan in response to that question, which is, I don't think with my gut. And so my response when I'm asked about that question is that, and I'll throw this to you too, because I really want to hear your answer, but I've had the great opportunity to explore planet Earth in all sorts of extreme environments. And based on my experience with the incredible diversity and tenacity of life on Earth, I'm optimistic in making the prediction, because that's what we as scientists do, the prediction that if conditions comparable to our own ocean exist on worlds like Europa, and if the origin of life is relatively easy, then we may well find life within Europa's ocean. And so with Earth as a guidepost, I'm relatively optimistic that we will find life somewhere else in our solar system and potentially beyond. How about you?
Yeah, I would play the probability game, right? So not thinking necessarily within our own solar system, but the potential for habitable places in other galaxies, right? And when you start to run the numbers of just how many potential Earth-like worlds there are out there, we will never get to them, but I would say, you know, the kind of intelligent life I think about is sort of the microbial life, and you know, it's all about, again, about perspectives, but they have completely terraformed our planet over billions of years. They are the master chemists, the master engineers. They build cities in the form of biofilms. They do electrical conduction at a distance. I mean, all of the crazy things that you would attribute to a well-oiled society you have going on at the micron scale. So if you take those as your aliens and you sort of run the infinite possibilities that are out there, I'd say the chances are pretty good.
But so given the extraordinary microbes that you study in your lab, do you think the origin of life is easy or hard? Rare or common?
I don't know.
That's a great answer.
No.
Yeah.
Yep.
Well, here's an interesting one. Is there any work being done to prove there isn't life anywhere except Earth? If not, do you feel like the search for life is hindering preserving Earth?
Interesting two-part question there. So all of our missions that go to explore potentially habitable worlds could well have a null result. And that results, you know, if we do find that life does not exist beyond Earth, that is an incredibly profound and important result. You know, as I say in the book, and as exemplified by this image here, let's see. Yeah. So this image, drawn by the hand of Galileo over 400 years ago, shows Jupiter at the center, that wheel shape. And then the four bright dots are what he observed when he first turned his telescope to the night sky. And when Medici first jotted down these stars and stuff, he thought they were just stars that were not visible in naked eye, and with his telescope he was able to then see them. And so he called them the stars of Medici, because the Medici family was funding his research and he was not an idiot. But night after night, Galileo tracked those small little points of light, and he saw that they moved, and that, of course, was heretical and got him put under house arrest by the Inquisition. But with Galileo's careful mapping of what would come to be known as the moons of Jupiter, those four dots there, Galileo put the final nail in the coffin of Aristotelian cosmology and opened the doorway to the Copernican revolution. And in the decades and centuries afterwards, we would come to appreciate, thanks to drawings like this, that the laws of physics apply not just here on Earth, but also to worlds and wonders beyond Earth. And then with the advent of spectroscopy, we would come to appreciate that the principles of chemistry work not just here on Earth, but also on worlds and wonders beyond Earth. And then with the space age and sending robots to Mercury and the Moon and Mars, et cetera, we would come to appreciate that the principles of geology work beyond Earth. But when it comes to that fourth fundamental science, physics, chemistry, geology, and biology, when it comes to the fourth fundamental science, we have yet to make that leap. We do not yet know whether or not biology works beyond Earth, or if biology is just some sort of biological singularity that arose here on Earth and the rest of the universe is devoid of life. And part of what excites me about the time in which we live and the capabilities for exploration and discovery that we now have is that for the first time in the history of humanity, we can push that frontier and ask those questions and potentially discover life beyond Earth, bringing the universe to life, discovering that we live in a biological universe, which is a profound result. Or if we go for many decades and find no sign of life anywhere within our solar system or on exoplanets well beyond our solar system, if we find not a peep of microbe or alien spaceship, that turns the telescope back on us and really underscores how fragile biology may well be, and it really emphasizes how much we need to take care of our home planet and protect the biosphere that is here.
That question, or that last comment of yours, really leads into this question here. What are the biggest lessons the space science and space tech communities can learn from the ocean to community? And I guess for both of you then, and what can the ocean community learn from the space community?
You got any ideas?
Certainly from the technological standpoint, I think there's a lot of potential for innovation and crosstalk between the fields, as we were just talking about. And the ability to use autonomous technologies is really going to, I think, open the door for better understanding our planet. It is difficult to get into the deep ocean. We can't study it like we can with satellites. We don't know a lot about the surface of our planet in the terrestrial world, but once you hit water, that light penetration doesn't go very far, and so we're sort of limited to other types of technologies, and places like JPL really thrive at innovating and developing these sort of autonomous systems that would allow us to measure and explore and do things in ways that are highly distributed and very impactful for our science. So, yeah.
And I think ocean exploration, certainly for Europa and more broadly for the search for life, scientifically, it serves as a foundation from which we, on the space exploration side, can then leverage and then develop instrumentation that can look for things that might be indicators of life. So a great one that you and I talk about, my colleague Owen Reeves, who's in the audience, focuses on this also, is methane, right? What should we look for on a world like Europa or Enceladus or Mars, for that matter? What are kind of the canaries in the coal mine for biosignatures, for signs of life on these worlds? And compounds like methane that come out of hydrothermal vents that are produced by various microbes that Victoria studies. These discoveries and various products of life inform how we approach the search for life on worlds like Mars and Europa. So there's some really interesting kind of handshakes that occur scientifically that help make sure we're on the right track and not, sniffing out some compound that has no relevance to life as we know it.
Yeah. Yeah.
What are your thoughts on life that isn't carbon-based, that may not need oxygen? What do these look like to you?
I honestly cannot conceive of them at this point. This comes back to Saturn's moon Titan, where on Titan, the liquid methane would potentially be the solvent. So instead of, we're fancy bags of water, from the tiniest of microbe to the largest of organism, we are predominantly water-based life, and we dissolve organic compounds and some compounds we don't dissolve, but basically we're a soup, and the main part of the soup is water. On Titan, the main soup is liquid methane, and I guess I'm just not clever enough to think of like how you would make that life happen. If you look at the periodic table, some people say, well, can't you make silicon-based life given the valence of silicon? The problem there is that geology has already showed us what happens with organization of silicon. That is geology, that's mineralogy, that's gems. Our mantle is full of silicon arranged in all sorts of sheets and various structures. So I kind of have a hard time imagining silicon-based life or even Silanol-based life. But there again, maybe Mother Nature has a much more creative solution than we can think of. Can you think of anything?
Water's pretty
Useful.
magical.
I wish we could finish this. One or two more questions here, but I'm going to actually let Victoria, if you have any last questions that you wanted to pose before we close the evening.
Do you have any other books that you're planning on writing?
Well, one of the sort of Saturdays of writing this book, Alien Oceans, was when I gave the draft to my brilliant editor, and she eventually got it back to me and said, get rid of this 100 pages. And so I've got 100 pages of unused material from this book that goes into much more detail. You and I have talked a bit about this, thermodynamics and Gibbs free energy and stuff. So that might be it. But I also am very passionate about critical thinking skills, the ways in which we do and do not adopt critical thinking in our everyday lives. And I think that's an incredibly important topic right now. And so perhaps that book might take precedence.
Well, thank you. I do want to remind everybody there will be another Behind the Book. It's written by Julie Newman. The book is Pull, Don't Push, and it is dealing with getting more girls into science, dealing with the K through 12 education that will encourage them as young women to come to and apply to places like Caltech. Though this first-year class is the first-year class with more women than men at Caltech. And so with that, reminder that we're going to be selling the books out in the lobby. Kevin will be there to sign them. And would you all help me thank both Kevin Hand, Victoria Orphan for a wonderful evening.